If you've ever driven past a major refinery or a petrochemical plant, you've undoubtedly seen them. I'm talking about those massive, towering steel structures reaching up into the sky like metallic skyscrapers. These are distillation columns, and they are quite literally the vertical cities of the industrial world. But have you ever wondered how on earth you actually design the intricate piping and mechanical layout for something so enormous? Well, in today's explainer, we're going to explore the immense scale and the highly structured engineering required to make these giant towers function safely and efficiently. Okay, let's dive right into this. Just looking at the majestic scale of these industrial columns, it's wild to see how heavily congested they are with ladders, platforms, and just miles of snaking pipes. Throughout this explainer, we are going to demystify this incredibly complex mechanical layout. We'll break down the process engineering that's happening inside that steel shell, and then we'll look at the strict, almost architectural rules that piping designers use to route these massive networks. Here is our roadmap for this macro to micro journey. We'll kick things off with the art of separation, take a look inside the column, cover the piping study prerequisites, move on to mapping the tower, and wrap up with access and maintenance needs.
All right, Section 1, the art of separation. To really get started, we need to understand what these towers are actually doing out there. While they come in all sorts of shapes and sizes, their core functions usually fall into mass transfer operations, like distillation, absorption, and fractionation. Let's ground ourselves in the fundamental physics happening inside. Distillation is formally defined as separating the constituents of a liquid mixture through partial vaporization and then separately recovering the vapor and the residue. But simply put, we're just using heat and gravity to force a mixed liquid to separate into its individual, purified parts based on exactly when they boil.
It's a brilliant dance of physics, really. Because of the difference in gravity between the liquid and vapor phases, the heavier liquid runs down the column, cascading downward from tray to tray. Meanwhile, the lighter vapor is rising up the column. As they pass each other, they're forced into intimate contact on every single tray, which is exactly what allows that mass transfer to happen. Now, when we're dealing with an incredibly complex mixture, like crude oil, for example, we use a highly specific type of distillation called fractionation. As the crude feed enters the column from a furnace, it flashes because of a sudden release of pressure. As those vapors rise and the liquid falls, heavier components condense while lighter ones vaporize. This is a process called refluxing, and it's so precise that it establishes a distinct temperature distribution throughout the tower, allowing engineers to draw off specific cuts, things like naphtha, gas oil, and heating oil, all at different elevations. Moving right along to Section 2, inside the column. So we know the chemistry, but how do you physically force a rising gas and a falling liquid to mix efficiently? Let's zoom in on the belly of the tower. There are essentially two main categories for the mechanical internals: plate columns and packed columns. Packed columns use beds of specialized structural packing material to create a ton of surface area for the liquid and vapor to interact. Plate columns, on the other hand, which are incredibly common, use a series of precisely spaced stacked trays. The lighter hydrocarbons vaporize and actually flow up through holes in these tray plates, making direct contact with the liquid resting right there on the tray. And I gotta say, the specific mechanism of bubble cap trays is just fascinating engineering. The vapor doesn't just casually drift through a simple hole. No, it rises up through tiny risers into a cap, and then it's forcefully pushed out through slots as tiny bubbles directly into the surrounding liquid pool on the tray. Then that liquid flows over a weir and down a downcomer to the next tray below. It's literally a highly controlled, cascading waterfall of chemical reactions. All right, Section 3, piping study prerequisites. With the internal mechanics making sense, let's shift our perspective over to the control room. Before a piping designer routes a single line of pipe around this massive structure, they need a very specific set of documents. This checklist is practically mandatory. It's the designer's foundational toolkit. The P&ID gives you the process data, the plot plan dictates the tower's physical relationship to other equipment and main pipe racks, and the fabrication drawings give you the exact diameter, height, and locations of those internal trays we just talked about. You simply cannot design a vertical city without fully understanding the required equipment elevations, pipe sizes, and operating conditions first. Which brings us nicely to Section 4, mapping the tower. Armed with that toolkit, we transition into the actual layout phase. This is where the magic really happens. We're stepping into a full-on urban planning exercise, mapping out the traffic lanes and access points of our vertical city so everything operates without crashing into each other. It's a highly systematic sequence. First, the designer essentially draws all that P&ID data right onto an elevation view of the tower.
Second, they orient the doors, which are the manholes. Third, they visualize the highways, the pipelines routing away from the tower. And fourth, they align all the structural brackets to hold the whole shebang up.
Handling access is totally crucial here, which brings us to an absolutely ironclad engineering law. Manholes shall be oriented towards a dropout area within a 30-degree segment of the column. Now, why is this so incredibly strict? Well, during a shutdown, maintenance crews actually have to pull those heavy internal trays and bubble caps entirely out of the tower. They desperately need a clear, unobstructed vertical drop area so they can safely lower those heavy internals by crane down to the main access way at ground level. So, once the manholes clean their 30-degree segment, we have to route the pipes. Let me introduce you to the 180-degree routing rule. If a pipeline has valves or instruments, it obviously needs to be near a platform so a human operator can actually reach it. But if a line is just a straight run of pipe heading straight out to the yard or a pipe rack, designers optimize the whole layout by placing it on the 180-degree segment. That's the complete opposite side of the tower, as far away from the manhole platforms as physically possible. Finally, Section 5, Access and Maintenance Needs. We've talked a lot about satisfying the process chemistry and routing pipes, but we absolutely cannot forget the human element here. Operators and maintenance crews have to safely service these absolute behemoths. So, here are the golden layout rules that exist entirely to satisfy human maintenance needs. First off, you can never locate a manhole opening directly into a downcomer section. Otherwise, the crew literally couldn't get inside. Any manhole 12 feet or higher requires a permanent access platform. We also have to supply utility stations with steam and air right on those platforms to power maintenance tools. And we have to ensure structural handling davits are perfectly positioned to lift the really heavy components.
Because remember, the column does not exist in isolation. It's part of a much larger ecosystem. All of this meticulously planned piping must ultimately run down from our vertical city and connect flawlessly to heat exchangers, reflux drums, and massive pumps just waiting at grade level. The alignment of a tiny nozzle 100 feet up in the air directly impacts the suction line of a pump all the way down on the ground.
But that leaves us with one incredibly vital, invisible factor. Think about this. As these vertical cities process boiling liquids at the bottom and high-pressure vapors at the top, the massive steel shell and all the attached piping will physically expand and grow inches in length due to the heat. So how must this static, rigidly mapped piping flex, expand, and move to survive that extreme thermal stress without just tearing the tower apart? That absolutely fascinating world of piping stress analysis is exactly what we're going to need to explore next time. Keep that in mind as you process everything we've uncovered today.